We are going to say about number systems. In the earlier classes, we have know that how to represent the various types of numbers on the scales or in the number line. It is simple, nothing but in a scale where it is 1, 2, 3, as well as -1, -2, -3. Positive as well as the negative values are marked here. Okay, just imagine we are walking from a 0 to some other unknown values, as well as in the positive direction as well as in the negative direction. It is in number line. In the earlier classes we have learned that we can mark or how to represent the various types of numbers in the scale. Okay, in this number systems, and briefly we are going to see how the rational or irrational numbers are going to be marked in the number lines. Okay, there are variety of numbers. Okay, from it will starts from the 0, 1, 2, 3 as well as the -1, 1/2, like that. There are natural numbers. Natural numbers means it starts with 1, 2, 3. There is no zeros in it. If it is a whole number, there be a 0. Okay, it comes in a set where integers are denoted. Integers means next is an integers. Integers means 1/2, 3/4. It's also a -2005 by 2006. You can see these are all the negative integers, and these 1/2, 3/4 are the positive integers. The collection of rational numbers is denoted by q. Okay, the rational numbers comes from the word ratio, that is q being a quotient. That is the simply we can denote a rational numbers as r, which is r is equal to p by q, where p and q should be an integers, but q should not be equal to 0. Okay, because if it is an, for example, p be a 1 and q be a 0, 1/0, there is no meaning for the value of it. So q should not be 0 in any other cases. For example, if we consider -25, it can be also written as -25/1, as like that 1/1, 2/1, 3/1. Okay, here you can see 1/2, 2/4, 10/20, 25/15, and so on. These are all the equivalent ratio numbers. Here there is one example. Every whole number is a natural number. This statement is false because 0 is a whole number, but it is not a natural number. In previously I have stated that natural numbers starts from 1, 2, but it does not contain a 0, where 0 is a whole number. Likewise, every integer is a rational number. It is true because we have seen that p by q, m/1. Okay, so that every integer is a rational number. And previously we have seen some of the rational numbers, okay, which can be written as a p by q. Simply if it is a rational number, the term should be written as a p by q. If then now comes a irrational number, where if for example consider s as an irrational. If it is an irrational, it should not be written as p by q. For example, we consider √2. We can't able to write √2/1. There be the meaning or the value of the √2 will changes. So these are all of the types of irrational numbers. For example, √2, √3, √15, pi, 0.1. These are all of the types of irrational numbers. Then we are now comes one example. We want to locate a √2 on the number line. This is the problems given in the book. Just simply I am explaining that. Just put on one scale of line which contains 0, 1, 2, 3 as well as the -1, -2, -3. √2 by the Pythagoras theorem, it be written as 1 square plus 1 square. Okay, just mark 0 to 1 as 1 point. Just mark 0 and a, as well as we want to draw a perpendicular line from A to B as well as to O to B. There is the one point will come. Okay, mark that a point as an then take 0 as a center, mark the unit value be 0 to B, then cut the point as a 0 to B. Okay, this is the point, this is the value of the root 2 in the number line. Same like a root 3. I have solved this root 5 in the previous one. Next we are going to see about the real numbers and their decimal expansions. In the previous chapter we just without the decimals only we have calculated and also marked in the number lines. Here comes some of the examples where we are going to solve the problems using decimal expansions. Let us consider the small examples: 10 by 3, 7 by 8, 1 by 7. Find the decimal expansions. Just a simple division method. 10 we are going to divide this by 3. Here comes the values. Okay, same 7.0 by 8, 1 as well. Here you can see that a remainders begin 1, 1, 1 and 1. But here comes the remainder 6, 4 and at last it begins 0. In this case also at last it comes the 1. The remainders either become 0 after a certain stage or at the start repeating themselves. That you can see here. The numbers of entries in the repeating strings of reminders, they are being continuous ones. Here you can see 1 and the 1, and by using a decimal expansions we are putting in zeros. Here you can see that is a zeros. If the remainder repeats, then we get the repeating block of the digits. If whatever the values we substitute for 10 by 3, we will keep on getting in 3.333 and it will goes on. But if it is in a 0, here the conditions is stopped. If we get in a remainder as 1 or the other reminders, the value will be continuing. Here you can see it's a 3.333, it will continue. It's since it's 0, it stopped by the 0.875. The remainders of these values are keep on changing, so the values also keep on changing in this problem. There are certain cases we can see from these problems which we solved. Some in this remainders become 0 in some cases. The remainder never becomes 0. Here comes the rational and irrational differences. Here we can note that a point, the decimal expansions of the rational number is either terminating or non-terminating recurring. Okay. Moreover, a number whose decimal expansion is terminating or non-terminating recurrent, these are all the rational numbers. Other than these conditions are termed as an irrational numbers. So the property of irrational numbers similar to the property stated above for the rational numbers, but the difference is that decimal expansions of irrational number is non-terminating term. Here this is not terminating points, but here it is not non-terminating. That's the difference between rational and irrational in the decimal expansions. These are some of the solved problems. Here comes some of example for the irrational numbers. Here root 2 and pi be considered. Root 2 we know that it's a default value 1.414 as well as the pi 3.14. We often take pi values to be at 22 by 7, but it is not an equal to it. So the root 2 expansions we can get as 1.414. We solved this by stepping up the irrationals. 1 plus 1 by 3 plus 1 by 4 into 1 by 3. As like this goes on, its the values will be 1.4. This is stated by the Archimedes.